Welcome back to the Deep Dive. Today, we're taking on a mission that usually lives in the C-suite of engineering consultancies. We've essentially been hired.
That's right.
We're the chief systems engineer at a top firm, and our task is to build the ultimate roadmap. A complete engineering requirements specification, the SOR, and this is for a micro-EV platform that's got to launch everywhere. Europe, China, Japan, the US, all at once.
And that is a truly high-stakes balancing act. When you look at why these small vehicle programs fail, it's almost always the same thing.
What's that?
It's regulatory fragmentation. They're supposed to be cheap, compliant in totally different worlds, and safe. It's this core challenge that we call the micro-EV trilemma.
The trilemma, okay.
It's that extreme, sometimes completely conflicting pull between cost control, regulatory compliance, and system safety.
Right. And it's not like the normal car market, the M1 passenger cars, where things like crash safety are pretty much harmonized globally.
Not at all.
These little city runabouts, they live in this regulatory chaos. And that chaos, the huge gap between a European quadricycle and a Chinese annual car, that dictates everything.
Everything, right down to the physics. The voltage you choose for the architecture is decided by these rules.
So they're not just legal documents, they're hard physical constraints.
Precisely. They constrain mass, they constrain power, and by extension, they constrain voltage. If you design just for the super cost-sensitive EU market, you will fail China's safety rules. Period.
And if you over-engineer for China, you're way too expensive for Europe.
You've priced yourself out. You absolutely need a unifying strategy.
So what is that anchor point? If we have to build one single platform for all these different segments, from a little L6E quadricycle to a faster i0, what's the one strategic decision that gives the team a real head start?
Okay, so our core recommendation, the absolute foundation of this SOR, is a modular platform strategy. It's really the only way to manage this fragmentation without going bankrupt.
And what does that mean in practice?
It means we mandate an extensible high-voltage baseline. Specifically, we are targeting the 96-volt to 120-volt nominal architecture. That gives us enough performance headroom.
I see. So you build for the top end.
You build for the top, and then for the lower cost, lower power segments like that EU L6E, you use software derating and, some smart component simplification. But the core platform integrity, its safety, its performance DNA, that stays intact. Unifying that powertrain core is non-negotiable if you want any kind of scale efficiency.
Okay, let's unpack that regulatory complexity then, because it sounds like it dictates the physical DNA of the vehicle we're designing. We have to start in Europe, I think, with the L category. Regulation 1C8/2013.
Yes. And Lenny 688/2013 is so critical because it draws that first foundational line. Legally, these are quadricycles.
Not cars.
Not cars. In the eyes of the law, they are four-wheel motorcycles, and that classification is, well, it's a double-edged sword. It gives you these crucial exemptions from the really expensive M1 passenger car crash testing, but it imposes these incredibly strict limits that completely define your engineering approach.
Let's start with the lighter one, the entry-level machine that really defines the market, the L6EB, the light quadrimobile. What are the hard limits our engineers have to hit?
The big ones are twofold.
Yeah.
A max design speed of just 45 kilometers per hour, so slow, and a max continuous power of only 6 kilowatts. But the single most fascinating constraint from an engineering perspective is the weight paradox.
The weight paradox.
Yes. The mass in running order has to be 425 kilograms or less. But, and this is the crucial part of the regulation, for electric vehicles, this calculation explicitly excludes the weight of the traction battery.
Wait, the battery weight is excluded. That sounds like a huge gift for the designers. But what does that do to the rest of the vehicle? Does that mean the chassis and body have to weigh practically nothing?
That is the ultimate budget paradox. A modern lithium-ion battery, even a small 10 kilowatt or LFP pack for one of these, it can weigh 80, maybe 100 kilos.
Right.
If you had to include that, you'd fail the 425 kilogram limit immediately. You still need room for a driver, a passenger, the motor. So by excluding it, that 425 kilogram applies only to the body in white, the chassis, the interior, the motor.
So you're forced into extreme lightweighting.
Extreme. A traditional stamped steel body is just not going to work. It's too heavy. This is why all the successful L6E designs, they gravitate towards these highly engineered solutions. Tubular space frames, often in aluminum, paired with super thin, light thermoplastic outer panels. The engineering challenge becomes less about crash energy and more about pure mass reduction.
And that low power limit, the 6 kilowatt, that must have a direct impact on the cost structure.
Oh, a profound influence. That 6 kilowatt limit is the main reason a 48-volt low-voltage architecture is so attractive for this segment, like the Citroen Ami,
Why is that?
because the whole system stays under the 60-volt DC threshold, and that classifies it as SELV, or safety extra low voltage. The engineering benefit here is massive. You get to completely avoid all the expensive, complex, high-voltage safety components that are mandated by UN Regulation 100.
Okay, so what specific expensive bits do we to just skip by staying under 60 volts?
You skip the full high-voltage interlock loop, the HVIL, which is that continuous circuit that detects damage. You
Yeah.
skip the sophisticated insulation monitoring systems, or IMD, that check for current leakage.
Wow.
You can use simple cheap connectors, non-interlocked. Basically, you get to leverage this huge, mature 48-volt mild hybrid supply chain, which cuts a significant amount of cost and certification headache.
But our mission here is a global platform. And a 48-volt system, as cheap as it is, it just sounds like a dead end for performance. We have to look at the next step up, the L7EC, the heavy quadrimobile.
Right, and the L7EC is where the performance envelope really expands. The mass limit goes up a little to 450 kilograms for passengers, still excluding the battery. But the critical change is the power cap. It jumps to a pretty substantial 15 kilowatts continuous.
15 kilowatts. On a 48-volt system, that is a huge amount of current. We're talking over 300 amps continuously.
Exactly. You're pushing over 300 amps. You immediately hit the physical limits of copper wiring. The efficiency loss from heat, the I²R losses, would be enormous.
Wires would have to be like garden hoses.
They'd be incredibly thick, heavy, and just prohibitively expensive. And all that heat would mean you need a more complex cooling system for the motor and inverter. So the L7E segment, by its very nature, forces you to jump to a higher voltage, 72 volts, 96 volts, or more, which means you have to commit to full high-voltage safety from the start.
Before we leave Europe, there's another layer, Regulation 44/2014, anti-tampering requirements. This sounds less like building a car and more like building a digital fortress.
It's a critical requirement. It's designed to stop users from illegally modifying the vehicle, to go faster than 45 kilometers or to get more power than 15 kilowatters. That would violate its certification. So our SOR has to demand sophisticated anti-tampering measures baked right into the electronics.
So, for example,
The vehicle control unit, the VCU, and the motor control unit, the MCU, they can't just talk. They have to use an encrypted CAN bus handshake, a verification protocol.
so if I try to swap out the motor controller for some high-performance one I bought online, the vehicle should know.
It should know instantly. If the VCU detects an unauthorized controller, or if the software fingerprint doesn't match the original, the system has to go into a mandatory limp home mode, or even a full lockdown until a dealer can reflash it.
That's fascinating. And it's not just software.
No, you need physical checks too. The VCU has to constantly cross-reference the data from the wheel speed sensors against the motor's RPM.
Ah, that's clever. So if someone changes the gear ratio to get a higher top speed but doesn't touch the controller, that mismatch between wheel speed and motor speed would flag it?
Correct. Any discrepancy that suggests an unauthorized physical change to the drive ratio has to trigger a fault and cut the power. This level of security has to be in the SOR from day one. It affects the vehicle's legal status.
Okay, now let's pivot to the east, to China. The shift from those old, unregulated low-speed EVs to the formal ASRA class. This feels like a massive regulatory earthquake.
It is. China basically decided that their micro-EVs were not quadricycles. They were just small passenger cars.
Yeah, that's the single most important distinction for our engineering team, isn't it?
It is. The ASRA class, the Wuling Hongguang Mini EV is the poster child. It completely changed the engineering budget. These vehicles have to meet passenger car standards, not motorcycle standards.
Which means for passive safety, this is a total break from the EU L6E, which is built on those crash test exemptions.
Absolutely. The SOR has to mandate that our ASRA variant satisfies a full set of passenger car safety standards, specifically GB 2007-1. That's non-negotiable. It means budgeting for real crumple zones, for a high-strength safety cage.
So those simple thermoplastic panels on a tubular frame we talked about for the L6E,
They're just not adequate for China. Not unless they're heavily reinforced with expensive, high-strength steels in critical areas like the A-pillars and B-pillars. The weight challenge gets a lot harder when you also have to keep the occupants safe in a real crash.
but the real global benchmark that China is setting isn't just the structure. It's the battery safety standard, the upcoming GB 380031-2025.
This standard is truly transformative. We have to adopt it globally in our SRR preemptively. The core requirement is extreme. After a single cell goes to thermal runaway,
Right.
The battery pack must not experience fire or explosion for at least 2 hours.
Okay, let's just pause on that. The old standard was, what, 5 minutes of warning to get out?
5 minutes, just enough time to escape.
So moving to 2 hours of complete containment, that is a fundamental redesign of the entire battery pack.
It's a total overhaul. You're fighting the rapid spread of heat. When one cell goes, it generates immense heat and ejects hot, flammable gas. The 5-minute rule assumed you could get away. The 2-hour rule assumes you might be stranded. And the battery pack itself has to be the ultimate fire shield.
So you're building a tiny safe inside the car.
Essentially, yes. It forces you to use thermal barriers between cells to slow that heat transfer, to give the neighboring cells time to cool down instead of joining the chain reaction. It turns the pack from a passive box into an active thermal containment vessel.
What are the direct design mandates from that 2-hour rule for our SOR?
Okay, first, it almost forces you to use LFP, lithium iron phosphate, chemistry. NMC has better energy density, sure, but LFP is far more thermally stable. It just doesn't burn as violently.
Right.
Second, the packaging becomes hyper-engineered. We're mandating a cell-to-pack or CTP architecture, but inside it we require things like aerogel insulation pads between cell groups. And above the pack, to protect the occupants, we have to mandate mica protective layers to stop fire from burning through the cabin floor.
So we're not just monitoring the battery for fire, we're actively fireproofing the cabin against it.
Exactly. And the pack has to have designed directional venting. Explosion-proof vents that push all those hot gases outside the vehicle structure, away from where people might be trying to get out.
And there's a physical impact test, too.
Yes, a bottom impact or ball strike test. So our SOR has to mandate high-strength steel or composite skid plates under the battery to protect it from being punctured by road debris.
Okay, let's quickly touch on the other big markets. Japan and the US. How do they fit into this global puzzle?
Japan has its famous key car market, but for our Micro-EV, the most relevant category is the ultra-compact mobility class.
Right, like the Toyota C+ pod. And that class offers some flexibility.
A lot of flexibility. It's designed for lightweight, last-mile vehicles. So they're speed limited to about 60 kilometers, and they're banned from expressways. And because of that, Japan relaxes some of the toughest M1 safety standards.
Which gives us a legal path for our lightweight designs.
It does. It lets us use the thermoplastic panels we need for the EU weight targets, while still demanding proper internal structures for that lower speed.
And the US market. The FMVSS 500 low-speed vehicles, or LSVs, this seems like the easiest one to pass.
It is, but it offers the least utility. LSVs are stuck at 20 to 25 miles per hour. Think golf carts on a college campus. The big draw for manufacturers is they are exempt from all the rigorous crash testing.
But the big engineering warning here is that we can't design only for the US market.
Absolutely not. The SOR has to be clear on this. The US LSV requirements can't define our baseline. Our global strategy is built on meeting the tough demands of China's A-Literal and the EU's L7. The US LSV is just a derated, simplified variant of that robust core platform. It's not the target.
Okay, so with those boundaries mapped, we can get into the core of the SOR, the architecture. And the single biggest decision, the one that affects cost, performance, everything, is the voltage. 48 volt versus a higher voltage strategy.
This is the absolute nexus of that Micro-EV trilemma we talked about. How do you balance cost, performance, and compliance? The 48 volt case, the Citroën Ami strategy, is perfect for that low-speed 6 kilowatt EU L6E market.
Right, we covered the pros. It's SELV, under 60 volts, no expensive high-voltage safety gear.
It's the ultimate cost control play for that one. Very specific, very limited use case.
So why can't we, as this global consultancy, justify just building a dedicated 48-volt platform for Europe? It would be cheaper and faster.
Because of current and scalability. The second you try to push the power, anything over 10 kilowatts, the current just becomes insane. Over 200 amps. You need massive, expensive copper wires, and you're just wasting energy as heat. It's a dead end. It caps the vehicle's utility, and it fails to meet the needs of the L7E and Ager markets.
Which brings us to our strategic recommendation. The 96 to 120 volt case, like the Wuling Mini EV. We're mandating this globally, but I have to play CFO for a second here. If that EU L6E market is huge, doesn't the marginal cost increase of putting a 96-volt system in every single one of them hurt our business case? Does the scale really justify that extra cost on every unit?
It's the essential trade-off, and yes, I'm arguing the scale absolutely justifies it. We gain enormous supply chain efficiency by unifying the battery packs, the charging hardware, and most importantly, the motor controller. The 96-volt platform is what we need for the EU L7E and the Chinese HRN class. It gives us that 15 to 30 kilowatt performance for speeds up to 90 kilometer.
But hold on, the second you cross that 60-volt line, you're forced to install the full HV safety architecture, the HVIL, the IMD. Doesn't that just blow up the cost compared to 48-volt?
It increases the cost, yes, but not exponentially. And this is the critical engineering sweet spot. While that voltage, say 96 volts nominal, peaking around 115, does require full HV protection, it's low enough that you can use power semiconductors rated at only 150 volts.
And for our audience who deals with 400-volt EVs, that's a huge difference.
A staggering difference in cost. Mainstream 400-volt systems rely on these expensive, complex power modules with IGBTs, insulated gate bipolar transistors.
Which are costly, they're complex to drive, they need serious cooling.
Exactly. By staying below 120 volts peak, we can use commodity 150-volt rated MOSFETs. And MOSFETs are high volume, they're mature, they are significantly cheaper. The savings in the motor controller alone justifies the jump from 48 volts. It gives us performance, efficiency, and a controller cost that is low for the performance you get.
So the SR mandate is clear. Adopt the 96 to 100-volt nominal platform as the global baseline. Build for the top and derate for the bottom.
That's the strategy. It supports L7E and A0, and we use software to meet the L6E 6-kilowatt limit. It guarantees unification and scale.
Okay, let's lock down the physical budget. The EU L7E limits non-battery mass to 450 kilograms. What's our hard target for the body in white and the chassis?
To meet that 450 kilogram limit, but also have enough margin for the heavier crumple zones we need for China, we have to impose a really strict mass budget. We are targeting 350 to 380 kilograms for the body in white and chassis system, maximum.
That is incredibly aggressive. How do we hit that and still meet the A0 safety standard?
We mandate a hybrid structure. We take inspiration from the successful lightweight models, but we bake in the safety from China. So we require a tubular frame structure for the core safety cage, combined with thermoplastic panels for the exterior.
And that hybrid gives us what?
Low weight, some minor crash resistance, and really important for fleet buyers, it makes replacing panels super easy and cheap, which helps with insurance.
Dimensions are also a big deal, especially for cities in Europe and Japan.
Yes, the SRR has to specify a max overall length of less than 2,500 millimeters. That helps with Japanese ultra-compact certification and gives you a real parking advantage everywhere. And we're specifying a max width of less than 1,500 millimeters. These dimensions have to be locked down now. They constrain everything.
And finally, performance. We need to define what the hardware can do versus what the software allows.
Right. The hardware has to be designed to support a 90 kilometer top speed for L7E and L0. The key part of the SOR is mandating that for the 45-kilometer rate L6E market, this limit is enforced purely through software locking in the VCU, not by changing the hardware.
And gradability.
We need robust hill climbing ability. So the mandate is greater than 20% gradability when fully loaded, and that dictates a peak motor torque of at least 80 newton meters.
And range. We need a couple of tiers.
We define two main options on our standard 96-volt LFP platform. A base version with a small 5 to 7 kilowatt pack that should get about 70 kilometers on the WMTC cycle. That's for the typical L6E city user.
And a long range.
A long-range version with a larger 13 to 17 kilowatt pack. That needs to hit around 150 kilometers on the Chinese CLTC cycle. That makes it competitive in the A-liter market.
All right, let's move from the macro architecture to the specific subsystems. For a micro-EV, maximum integration is key, isn't it? To save every gram and every millimeter.
Absolutely. The SRR has to mandate an integrated power unit, or IPU.
Which means?
The requirement is for a 3-in-1 integrated E-axle. This unit combines the motor, the gear reducer, and the motor control unit, the MCU, into one single compact system. It saves a huge amount of space, simplifies the wiring, and lowers manufacturing costs.
Okay, motor type. Cost is everything, but we need efficiency. So PMSM or the cheaper ACM?
It's a tough call, but our SOR mandates a preference for an air-cooled permanent magnet synchronous motor, a PMSM. AC induction motors are cheaper up front, yes, but the superior efficiency of a PMSM, especially in city driving with lots of stopping and starting, means you need a smaller battery to hit your range targets.
And that battery saving often offsets the higher motor cost.
Often, yes. Our target is 15 kilowatts nominal, with a 30 kilowatt peak to make sure we hit that 20% gradability target.
And cooling for this integrated unit.
For the standard L6E and L7E versions, Just forced air cooling is probably enough. The power output is low. But since this platform has to scale up, the SOR must specifically pre-engineer the chassis and the e-axle casing to accommodate water cooling interfaces. For the higher performance Acer variants in China, you'll need liquid cooling for sure.
Let's go back to the battery system. Our safety mandate is clear. GB 38031-2025 is the governing standard, full stop.
It's completely non-negotiable. LFP chemistry is mandatory. And for packaging, we have to use a cell-to-pack architecture, no modules. It saves weight and boosts energy density, which is critical in these tiny cars.
And what about the internal protection systems, the things that bias that 2-hour fire containment window?
We're requiring detailed placement of aerogel inner cell padding. Aerogel is crucial. It has incredibly low thermal conductivity, so it slows down the fire spreading from one cell to the next.
And above the pack.
We mandate mica sheets or something similar, a flame retardant barrier right under the cabin floor to protect the occupants from burn-through.
That directional venting sounds like a tricky physics problem in such a small space.
It is a critical piece of safety engineering. The SRR specifies an explosion-proof vent design that has to push those hot, flammable gases safely outside the vehicle and away from the doors. You don't want someone trying to escape and running into a jet of flame.
The battery management system, the BMS. This needs functional safety. What ASIL levels are we requiring here?
For the most critical functions, so overcharge protection and over-temperature protection, the BMS hardware and software have to be developed to ISO 26262 ASIL C or D. This ensures the failure rate is incredibly low. A high integrity level here is an investment against a massive, costly recall down the road.
Okay, let's talk braking. This is a classic EV challenge. No engine means no vacuum.
A point that a lot of low-cost EV startups miss. Traditional brakes need a vacuum booster, so the SRR must explicitly specify an electronic vacuum pump, an EVP, combined with a vacuum reservoir. That ensures you always have consistent, reliable brake assist.
And the regulations for braking are different, too.
Yes. The EU L7E requires either ABS or a combined braking system. For our global car, the SRR mandates a standard dual-circuit hydraulic system, but we are strongly recommending we standardize on ABS for all the higher trims.
Why?
On a car this small and light, with a short wheelbase, ABS is a vital safety feature for stability during an emergency stop, especially on wet roads.
And regenerative braking. The VCU has to manage this complex hybrid braking logic. What's the key safety mandate to prevent a sudden loss of braking power?
The VCO has to constantly blend regen braking with the mechanical friction brakes. But the key safety requirement is this. When the battery is full, say over 95%, or when it's very cold, it can't accept much regenerated energy.
Right.
In those specific cases, the mechanical brakes must be able to provide 100% of the required stopping power, with zero help from regen. This prevents a driver from getting a nasty surprise when they leave their garage with a full battery and the brakes feel weak.
Let's move to the digital core of the vehicle, the EE architecture, and specifically the Vehicle Control Unit, the VCU. Functional safety has to be foundational here.
Absolutely. The SOR has to specify high-integrity hardware. We're recommending automotive-grade MCUs, like the NXP S32K or Infineon Oryx series, specifically because they feature lockstep cores.
Lockstep cores. That sounds like a military term.
Yeah.
For our listeners, what exactly are they doing and why are they mandatory for safety?
Think of it like having two brains doing the exact same math problem at the exact same time. You have two identical processing cores inside the chip. They run the exact same instructions simultaneously. A comparator circuit constantly checks their results.
And if they don't match?
If the result from core A is different from core B, even by 1 bit, the system instantly knows there's a hardware fault. Maybe a cosmic ray hit it, or there was a voltage fluctuation. It immediately triggers a fail-safe state before that fault can cause a dangerous outcome. This kind of intrinsic redundancy is non-negotiable for systems controlling torque or braking.
So what are the VCU's main jobs in this Micro-EV?
It has 3 core duties. First is torque arbitration. It takes the driver's pedal input, checks it against the battery's limits, the motor speed, and the anti-tampering rules, and then it sends the final safe torque command to the motor. It's the traffic cop for power.
Okay.
Second, it integrates all that anti-tampering logic we talked about. And third, and this is crucial for safety, is managing faults.
You mean the limpo mode?
Exactly. The SOR defines this for non-fatal faults, like a sensor failing or a temporary communication loss. Instead of just shutting the car down, which could be really dangerous, limp home mode limits the power, maybe to 20 kilometers. It keeps the car moving so the driver can get to safety.
Let's formalize the functional safety targets. The ISO 26262 ACL levels. Why are some higher than others?
We break it down based on severity and controllability. For unintended acceleration, the target is ASAL B or maybe C. It's dangerous, but the driver can usually brake. For unintended braking or locking, though, that could cause a spin. The driver has much less control, so the target has to be higher, ASAL C or D.
And the high voltage system itself.
For high voltage shock risk, especially in a crash, the target is ASIL C. That ensures we have high diagnostic coverage to detect any current leakage before it becomes a hazard. Defining these levels now means every supplier has to meet the same rigorous standard.
The digital threat is just as real as the physical one now. So we need to bake in cybersecurity. Which standards are we mandating?
Mandatory compliance with the new UNES regulations. That's UN R155 for cybersecurity management and UN R156 for software updates, plus China's own standards. Security cannot be an afterthought.
So how do we actually implement that in the VCU?
3 layers. First, secure boot. The VCU hardware can only execute software that has been verified with a digital signature. Second, diagnostic protection. You can't just plug into the OBD port and change things. Write access has to be protected by a seed and key authentication process.
And protecting over-the-air updates.
That's the R156 part. All OTA updates have to be encrypted and digitally signed to prevent attacks. The VCU has to verify that signature before it installs anything. This protects the car, and just as importantly, it protects the future revenue from software features.
Verification. Physical crash testing is slow and expensive, which is the enemy of a low-cost Micro-EV. We need to leverage virtual testing, or CAE.
This is a massive strategic advantage, and we have to exploit the rules that allow it. EU Regulation 168/2013, Article 32, specifically permits using computer simulations to replace certain physical tests. It's a game changer.
What kind of tests can we do virtually?
Mostly structural integrity tests where the physics are well understood. Things like rollover protection strength, seatbelt anchorage strength, even some energy consumption modeling. If you have to physically crash test every single variant of your platform, you'll go broke.
So what's the financial saving we're mandating here? Can we quantify it?
We are talking about substantial savings. A single physical structural test can run you $500,000, not even counting the prototype vehicle. If you have 2 main variants, passenger and cargo, plus a mid-cycle refresh, you're looking at 8 of those expensive tests.
So instead of 8 physical tests, what does our SOR say?
It says the team will build and maintain high-fidelity CAE models using tools like LSDYNA. The critical step is correlation. You do 1 physical test for each main design, just 1. You use that data to fine-tune and validate your computer model.
I see.
And once it's correlated, you can then use the simulation reports for certifying all the subsequent variants. This strategy can easily save over 30% in direct development costs and slash your time to market.
Okay, as we wrap up the SOR, we have to look at the competition. We need to benchmark our strategy against what's already out there.
Right. We need to analyze the 3 main strategies in play today.
Let's start with the market leader, the Wuling Hongguang Mini EV from China, the Aviara champion.
The Wuling's strength is its mastery of the performance-to-cost ratio. It used that 96-volt architecture, hitting that 150-volt MOSFET sweet spot we talked about. That let it offer real A0 highway capability, up to 100 kilometers, while being incredibly cheap. It proved customers will pay a little more for that extra performance headroom.
Contrast that with the European king of cost-cutting, the Citroën Ami.
The Ami is a perfect case study in engineering to the absolute lowest legal limit. It's strictly 48 volts, which avoids all the HV and crash safety costs. They even use clever tricks like symmetrical body panels to cut tooling costs.
But the trade-off is huge.
It's an extreme trade-off. That 48-volt structure gives you no viable upgrade path to the L70 or A0 performance you need for global scale. Our strategy has to avoid that limitation.
And finally, the specialized Toyota C+ pod in Japan.
The C+ pod shows a different focus. It's all about extreme energy efficiency and high safety for its class, mostly for business fleets. It uses a slightly higher 177-volt architecture, but keeps speeds low. It's a great example of how to do lightweighting with plastic panels, but still integrate serious internal crash structures for city use.
Okay, so taking all of that into account, let's summarize the final unified strategic recommendations, the definitive mandate from our consultancy to the engineering team.
There are 4 core mandates in this final SOR summary. These define success for a global micro-EV.
Number 1, platform unification via 96V.
We mandate the 96 to 100-volt nominal voltage architecture globally. It supports the performance we need for the growth markets, L7E and A0, and it maximizes our supply chain efficiency. That slight cost increase on the entry-level L6E is an acceptable price to pay for the massive gains in R&D focus and manufacturing scale.
Number 2, safety design preemption.
We tell the team not to wait for local rules. The battery system must be designed from day one to the tough GB 38 or DRIO 3031-2025 no fire, no explosion standard, and we embed ISO 26262 ASIL B, C, and D processes from the very beginning. This aggressive safety stance is the only way to be globally marketable and avoid a financially ruinous recall.
Number 3, aggressive virtual certification.
The team must treat virtual testing, CAE, as the default path for certifying structural variants. We exploit that loophole in the EU regulation. We only use physical prototypes for initial correlation. That's how we cut development time and cost.
And the final mandate, number 4, security integration.
The anti-tampering logic from the EU and the UN R155 cybersecurity frameworks have to be foundational to the VCU. It must be designed to detect and prevent unauthorized mods. This protects the car, and it protects our future business model for software services. So this engineering requirement specification, it's a comprehensive navigator. It's not just a checklist. It's a strategy to ensure the micro-EV we build isn't just drivable, but is intrinsically legal, safe, and globally competitive.
That's a powerful and incredibly detailed mandate. We started this deep dive talking about a chaotic regulatory zone, but what's emerged is a really clear path driven by safety and efficiency. This path is forcing the global micro-EV to adopt a 96-volt architecture, integrated e-axles, and full functional safety.
Absolutely. They're adopting the complex technologies that were pioneered in mainstream EVs, things like lockstep cores and cybersecurity, just scaled down to fit their smaller performance envelope.
So the provocative thought we'll leave you with is this. Given that these regulatory pressures are forcing micro-EV systems to become these high-integrity, high-efficiency 96 to 120-volt architectures, how close are they really getting to mainstream 400-volt EVs in terms of engineering complexity, even if their size stays tiny? If their underlying system complexity is almost at parity, where will the next generation of drastic, game-changing cost savings in the EV market actually come from?
Something to mull over as the whole automotive map continues to shift.
That's it for this week. Thank you for diving deep with us.